Today we're going to look at section 2.1, which is called Basics of Functions and Their Graphs. So we have quite a few objectives. We're going to find domain and range of a relation. We can determine whether a relation is a function. We're going to determine whether an equation represents a function. We'll evaluate a function, and then we'll graph functions by plotting points. So the definition of a relation. A relation is any set of ordered pairs. The set of all first components in the ordered pairs is called the domain. And when I say first components, we are thinking about the first thing in our ordered pair. Well, remember, in an ordered pair, you have x's and you have y's. X is first in the ordered pair, so domain deals with the x values. The set of all second components is called the range of the relation. So second components meaning the second term in our ordered pair. So y is dealing with the range. So we're going to find the domain and range of the relation. So notice that it's a relation because we have a bunch of ordered pairs. So to find our domain, we are going to basically identify all of the x values in our ordered pairs. Now, how we write it is we're going to have it with our little, oops, if my pen will work, with our little bracket. And then I like to go in order from smallest number up to biggest number. So if I scan all the values that are the x's in my ordered pairs, it looks like they happen to go in order of from the left to the right. So 5 is the first number, that's the smallest, 10 is the next x value, followed by 15, 20, and then 25. So there is my domain. So then my range is dealing with all of the y values. So once again, we're going to write it where we have our little bracket. And then once again, it's the y values. I want to go from smallest to biggest. Happens to be that it looks the same here as well. So 12.8 is the smallest number, followed by 16.2, 18.9, 20.7, and 21.8. Now, it's not always going to be in order like it is here. So just realize you are going to have to scan those ordered pairs, go from smallest to biggest. So let's talk about what a function is. So it says a relation in which each member of the domain corresponds to exactly one member of the range is a function. Okay, so each member of the domain goes to exactly one member of the range. So each x value goes to exactly one y value. That makes it a function. So we're going to look at these ordered pairs. We'll look at the relations, and we're going to determine whether or not we have a function. So if I look at this first one, we've got the ordered pair 1, 2, 3, 4, 5, 6, and 5, 8. So if you notice that in order to be a function, each x goes to exactly one y. Well, the fact that we see x is repeating itself here, I see a 5 twice, and if you notice that it goes to two different values. One of the 5s goes to 6, one of the 5s goes to 8. So because that same x value goes to two different y values, this would not be a function. If I look at the next example, we've got our relation with the ordered pairs 1, 2, 3, 4, 6, 5, and 8, 5. So as I see, every single x value is different. It is okay that the y's over here, we've got two y values that are the same number. But remember, to be a function means every x goes to exactly one y. Well, every x value is different, so it's okay that these 6 and the 8 goes to the same y value. This one would be a function. So now let's talk about functions as equations. So functions are usually given in terms of equations rather than a set of ordered pairs. So here's an example of an equation. Y equals negative 0.016x squared plus 0.93x plus 8.5. So some kind of equation, we can determine whether or not we have a function. So once again, for each value of x, there is one and only one value of y. So this time it might be a little bit harder to see right off the bat because with ordered pairs, remember each x has to go to a different y. Here, if we have an equation, we're not going to be creating every single ordered pair that's in that equation. So we're going to have to see how we're going to go about this. We call the value x the independent variable, y is the dependent variable, okay? Because essentially we are in these functions, we can substitute any value in for x, and then the y value is going to depend on the number that we substituted in. Just like not every set of ordered pairs defines a function, neither can equations. So we're going to be talking about how can I look at an equation and determine, yes, it's a function, no, it is not. So we are going to look at these examples. The directions say to solve each equation for y, and then determine whether each equation defines y as a function of x. So if I look at this first example, we have 2x plus y equals 6. Well, to get the y by itself, I'm going to subtract the x term over to the other side. And so I get y equals negative 2x plus 6. So if we think about what kind of function this equation represents, looking at the value of x, notice that its exponent is technically a 1. That makes this a linear function, okay? So it's not that you have to define what kind of function you have, but it is a linear function here, or linear equation, I guess. So what's going to happen is we are going to think about it. If I was to plug in numbers for x, is there ever going to be a time that I repeat and get the same value for y if I plug two different numbers in for x? And hopefully you understand that when you're dealing with a line, you're never going to plug in a number for x and get two different values for y. It'll just be one value. So that means that y is a function of x. Okay, because once again, the moment I plug one number in for x, I will only get one value for y. I will not get two different values of y. If we look at the second example, we've got x squared plus y squared equals 1. So if I want to start solving for y, I'm going to subtract the x squared over to the other side. That then gives me y squared to equal 1 minus x squared. We still don't quite have the y by itself. To get rid of the square, we are going to take the square root. So now if we remember what we just talked about in the last chapter, when you're solving an equation and you take the square root of both sides, you don't just have one answer, you have two. So we have both positive and negative, the square root of 1 minus x squared. So hopefully we notice here that if I was to start plugging in numbers for x, because there's this plus or minus sign thrown outside of it, it doesn't matter what value I get that square root to be, I'm going to have two solutions. So it's telling us that the moment I plug in one number for x, I get more than one value for y. So because of that, y is not a function of x. So I would ask that you pause the video, see if you can find the domain and range for the relation in number 1, and then solve for y in number 2 and determine whether or not y is a function of x. So hopefully you did the problem, you saw that, okay, all of the x values are my domain. So once again, I like to go from smallest to biggest. So -3, 0, 1, and 2. And notice that I have them in the little brackets. My range, all the y values going from smallest to biggest would be -11, -5.1, -4, and 6. Once again, it's in the brackets. Number 2, when you solved for y, you just had to move that 4x squared term over by subtracting and then divide every single term by a negative. So the moment I got the y by itself, I didn't have to, if I started thinking about plugging in values for x, I'm only going to get one value for y, so that means that y is a function of x. All right, let's talk about function notation. The special notation f of x represents the value of the function at the number x. We say we have the function f of x equals negative x cubed plus 1, and we are interested in finding f of negative 1. So to do that, we are going to evaluate the function at negative 1. So notice that because normally it's read f of x, and here we've got a negative 1 in the place of x, that's why below I've demonstrated that we are going to replace negative 1 with wherever we see an x. So I kept the negative from the outside, then I have in parentheses negative 1 being raised to the third power plus 1. So if you cube a negative, it's going to stay negative, but then because we have back-to-back negatives, it becomes positive. So we have 1 plus 1 is 2. So essentially then f of negative 1 equals 2. So let's look at a couple of examples. If we're given f of x equals x squared minus 2x plus 7, we're going to evaluate each of the following. First, we'll do f of negative 5. Then we'll do f of the quantity x plus 4, and then we'll do f of negative x. So once again, what this means is that whatever I see in the parentheses here is going to go substitute into each of the x's in the function provided. So we will have in parentheses negative 5 squared minus 2 times in parentheses negative 5 plus 7. So when I start simplifying, negative 5 quantity squared is positive 25. Back-to-back negatives, negative 2 times negative 5 is positive 10. Then we are adding 7. So if I add all of those numbers together, we're going to get 42. So I would write it as f of negative 5 equals 42. So there is our function at negative 5. In part B, I'm going to substitute in x plus 4 wherever I see x in my function. So in parentheses, we'll have x plus 4 quantity squared minus 2 times the quantity x plus 4, and then plus 7. So remember, we are squaring x plus 4, which means I'm going to write it as x plus 4 times x plus 4. Don't just square the x and don't just square the 4. You'll lose some terms. The negative 2 I'm going to distribute to get rid of the parentheses in the middle. So negative 2 times x is negative 2x. Negative 2 times 4 is negative 8. We still have plus 7. Okay, I'm going to distribute to get rid of the two binomials in the front. So x times x is x squared. Then we have a 4x. Then we have another 4x. And then we have a 16. So notice how those x's in the middle, we would have lost them if we just tried to square the x and square the 4. All right, so now we've got a bunch of like terms to combine. So we've got 4x, and negative 2x. So it doesn't look like there's anything to combine with the x squared, so I'll still have that. 4 and 4 is 8. 8 minus 2 would give us a positive 6x. Then we've got 16, negative 8, and positive 7. So when we add that, we're going to have 16 minus 8 is 8. 8 plus 7 is going to give us 15. And so this would be our function f of x plus 4. We get x squared plus 6x plus 15. And then same idea with this last one. I want to substitute negative x into every x in my function. So in parentheses, we'll have negative x quantity squared minus 2 times in parentheses negative x plus 7. Well, squaring negative x, so negative x times negative x. And negative times a negative is a positive, and we'll get x squared. Negative times a negative will give us another positive. So we'll have plus 2x, and then we'll have plus 7. Notice that there are no like terms to combine there, so we know that the function f of negative x is going to equal that x squared plus 2x plus 7. Let's talk about graphs of functions. So the graph of a function is the graph of its ordered pairs. We will be asked to graph multiple graphs on the same graph and then compare how the functions relate to one another. So we're essentially doing what we did in the last chapter. We're creating a table of values to make ordered pairs, but now we have more than one graph to do. So we're going to graph the functions f of x equals 2x and g of x equals 2x minus 3. So we'll do that on the same graph. And then we are asked, how is the graph of g related to the graph of f? So Like I said, we're basically going to be creating a table of values. So I'm going to be plugging in numbers for x, and we're going to substitute them in, and that will give us our y values, which essentially is this f of x function. So since f of x is 2x, I can substitute in some negative numbers, 0, and some positive numbers. So I'm just going to go from -2 to +2. So if I was to take then 2 times -2, I'll get that function to be -4. -1, substitute that in. 2 times -1 is going to give me -2. When I substitute in 0, 2 times 0 is 0. Substitute in 1, 2 times 1 is 2. Substitute 2 in, 2 times 2 is 4. So those are my ordered pairs for the function for f of x. So I'm going to plot those points. So -2, -4, -1, -2, 0, 0, 1, 2, 2, 4. Hopefully we notice that we do have a line here, which makes sense because that is just an x term, which makes it a linear function. So I'm even going to label that this is f of x. Because we're going to have two graphs, it's going to be important that we label which one is which. So now I'm going to make another table of values, and this is going to help me get my g of x function. Okay, so once again, I'm going to use the same numbers. I'm going to substitute those in, get my ordered pairs. So -2 times 2, when I substitute that in, is going to be -4, but then I have to subtract 3. So that's going to give me -7. -1 times 2 is -2, then I subtract 3, so I'll get -5. 0 times 2 is 0, when then I subtract 3, we get -3. 1 times 2 is 2, 2 minus 3 is -1. 2 times 2 is 4, 4 minus 3 is 1. So here are my ordered pairs. I'm going to go ahead and plot those points. So -2, we're at -7. -1 is -5. 0, -3. 1, -1. And 2, 1. So once again, notice how we formed a line, which makes sense because we once again just have an x. And so I'm labeling this as g of x. So then once again, the question says, how is the graph of g related to the graph of f? So notice that they are the exact same line as far as their slopes are concerned. They're increasing at the same rate. But notice that the g of x is below f of x. And notice that it's below by 3. So I would say that g of x relates to f of x by taking f of x and shifting down 3. Okay, because notice that they both had 2x in their function, but the g of x, whoa, that one, oh no, I don't know how to get my pen back. Sorry, guys. That -3 is why it's shifting down. Okay, got my pen back. All right. So let's talk about the vertical line test. It says, if any vertical line intersects a graph in more than one point, the graph does not define y as a function of x. So we've talked about determining if we have a function through ordered pairs, through solving for y and seeing if the value of x, if you input something, gives you one value for y. And now we're going to be able to, if I'm looking at a picture, how can I use this picture to determine if I have a function? So that's where this vertical line comes into play. Okay, so once again, if a vertical line intersects a graph in more than one point, the graph does not define y as a function of x. So here I have a couple of pictures. We're going to use the vertical line test to determine and identify graphs in which y is a function of x. So vertical line means I'm going up and down. So I can draw as many vertical lines as I want. If you notice that in this first picture, it's only intersecting at one point, or at one point, or at one point, or at one point. Okay, so each time it only hits one time. That indicates to us that we do have a function. Okay, so y is a function on x here because each time I drew that vertical line, I only hit that graph with the vertical line one time. If I look at the next problem, the moment I hit or draw that vertical line, notice that, hey, there's two spots that that vertical line hits. I can do that as many times as I want. I'm going to get the same result. So because this happens at more than one spot within the vertical line, this one is not a function. Okay, so I would suggest that you pause the video, try these two checkpoint problems. So you're evaluating the function at 4x minus 2, and then you're using the vertical line test to determine if y is a function of x. So with the first one, we're substituting that 4x minus 2 in for x. I'm distributing the 1/2, combine my like terms. So f of the 4x minus 2 equals 2x minus 11. If we look at the vertical line test, every single time I drew a vertical line, it only hit the graph one time, so y is a function of x. So that's us hitting all of our objectives. So we've talked domain and range. We've talked about if a relation's a function. We talked about the different equations that represent functions. We evaluated functions, and we graphed functions by plotting points.